Hi, and welcome to the TensorFlow course by Eduonics. This is our first tutorial, and in this, we're really just going to be getting started. We're going to be covering some of the foundations of TensorFlow. So let's take a look at the contents. In this video, we're going to be covering why TensorFlow, and for that section, we're pretty much just going to be giving you some suggestions as to why you might want to use TensorFlow instead of some of the other libraries out there. And then we're going to hit on tensors and tensor operations, followed by some of the main building blocks of TensorFlow. For the tensors and tensor operations, that's really just to help you kind of understand some of the basics, some of the smaller building blocks. Whereas the main building blocks is just to help you gain an understanding of the overall structure and what's happening within TensorFlow. And after that, we're just going to go into installation, and then we're going to run some examples. So let's go ahead and move on to why TensorFlow. TensorFlow is one of many deep learning libraries out there that can be used not just for constructing neural networks of different architectures, but building other models as well. So it's worth mentioning why you'd want to use TensorFlow over some of the others. To start with, it's widely used and it's well documented. It's quite popular. There are a lot of people that use it, which means that there are plenty of forums out there. If you run into any kind of bugs or you're just not quite sure how to do something, there's plenty of documentation in order to figure it out, to solve whatever problem you run into. And then aside from that, it's also easily deployable to production code. And by that, I mean production code as compared to just doing research on your own computer. The production code is used to deploy actual programs that run the TensorFlow models that you've constructed, that you've trained. Like, for example, if you want to create an app that has machine learning capabilities, then your TensorFlow code can be deployed to that production code easily, whereas some of the other libraries can create difficulties to do so. Also, because it's run by Google, it's updated quite often, which is very handy. If there's new research out there that shows new techniques, then it's more likely to be updated on TensorFlow first versus some of the other libraries. If you want to run your code on distributed computing systems or just cloud computing in general, the transition for that is made extremely easy. Whereas, again, if you want to do that with some of the other libraries, you may run into some complications. Getting it up and running, overall, extremely easy, both for the CPU and GPU versions. The GPU version is more comparable to Theano, because with Theano, sometimes you run into all kinds of random issues that can cause great headaches when you're trying to get it installed properly and up and running. It's just a bit easier with TensorFlow than something like Theano. And then, again, since we mentioned Theano, when you create a model with Theano, you first have to compile it. So every time you create something in code, you've got to compile it on the back end, and that compiles the graph and all the code for you. There's a bit of wait time there, it's not a huge deal, but with TensorFlow, there is no compilation time. And then, last but not least, there's TensorBoard. TensorBoard is kind of a big deal because it makes visualizing your graph extremely easy, and you can visualize other things about your model, such as how it's training, just overall performance, both during training and after. So that is a really handy API that Google offers with TensorFlow. And so let's go ahead and move on to tensors themselves. You can think of tensors as n-dimensional arrays. If you're already familiar with NumPy, then that's probably pretty intuitive to you. And one key difference is that they're measured by rank, which is really just saying what its dimensionality is. So if you look on the right, we have 4 different examples. We have the rank 0 tensor, which is a single element. That makes it a scalar value. And then we have rank 1, which is one-dimensional, so it's just a standard vector. And then rank 2 and rank 3. So rank 2 is a 2-dimensional matrix, whereas rank 3, you can think of that as being a stack of 3 2-dimensional matrices. 3 at least in this example, it could be more. But the point is, it's 3-dimensional. One thing to note about tensors is that unlike something such as pandas data frames, is that you have to have all of the elements be the same data type. So where with a pandas data frame, you can have some columns be integers, some be strings, some be float values, etc. In tensors, every single element in that tensor has to be the same data type. So they can be all integers, all strings, or all floats. And so now we can move on to the tensor operations. There are a lot of different tensor operations available with TensorFlow, so we're just going to cover some of the common operations. There are the elementary ones, which are the arithmetic operations. We have addition, subtraction, multiplication, and division. Those are all pretty straightforward. They just operate element-wise. So to give you an example, if you look at this matrix multiplication formula on the upper right, we have A, B, C, D, and alpha, beta, gamma, delta. So those are two different 2 by 2 matrices. If we were to add those together, then that would be element-wise addition. So we would have the result of A plus alpha and B plus beta, and then C plus gamma and D plus delta. So we'd be left with the same shape. We would have a 2 by 2 matrix with those elements added together. Same thing goes for the multiplication, division, and subtraction. Then we have the linear algebra type of operation, which is matrix multiplication. That's why we put the formula here, because not everybody's going to be familiar with it. So you can see with those 2 by 2 matrices that when they're matrix multiplied together, on the right-hand side of that equation would be the result. And that will give you some intuition as far as the operations that are being performed when doing matrix multiplication. And then there's something like dot product. While we're not actually going to show the formula for that, the reason it's mentioned is because it's actually a pretty common operation to be used. And then there's transpose. That one you may already be familiar with, but just in case, it's easy to illustrate because all it is just flipping the columns and rows essentially. So instead of having on the left-hand side a 3 by 4 matrix, then transposing it would give a 4 by 3 matrix. In this case, for the formula, we're showing the capital T on the right, so we're actually showing that the left-hand side is equal to the transpose of the right-hand side. So it's really just as simple as that. Like I mentioned, there are a lot of other operations within TensorFlow. Some of them are worth exploring, and some of them we will explore in later videos. Let's go ahead and move on to the main building blocks of TensorFlow. We're going to split some of the main building blocks of TensorFlow into two parts. We have lower level and higher level. The lower level components are really just lower level code. So they're more tedious to deal with. They're just kind of at a lower scale. Whereas the higher level, those are things that are already pre-built for you. They're built-in functions that make life easier, essentially. So on the lower level end, we have these basic building blocks. A couple of them we've already covered, tensors and operations. And then there's also graphs and sessions. The graphs and sessions, we're going to have to save the details of those for another video, but they're important to be aware of. Just to highlight them, graphs are basically all of the components of your model put together on the back end. They're written by TensorFlow and all of the connections between them, basically how everything connects. And sessions are where your program runs. So on the higher level end, we have loss functions, optimizers, layers, and estimators. We're going to cover all of those, but they're important to just kind of pre-mention here. Loss functions at their most basic level are really just functions that measure the differences between predicted values coming from your model and what those values actually should be. It's worth briefly noting that those functions are often differentiable, and that's really just because of how the optimizers work. It ends up being a requirement. There are a lot of different loss functions out there, and some of the most common types are mean squared error, log loss, cosine distance, and cross entropy. The mean squared error, you've probably already used that before. That one is often used for regression problems. Cross entropy actually has some subtypes. There's binary cross entropy and categorical cross entropy, as well as some others, but the first two are the most common. The differences between those is that binary cross entropy is used for binary classification problems. So if your model is just trying to predict between two different values, then the binary cross entropy is often a common or popular use. Whereas the categorical cross entropy is going to be used for anything that's classifying more than two classes, so 3 or more. And the formulas for those are just written slightly differently to account for the number of classes. And then we have log loss. That's actually really similar to cross entropy. We'd have to kind of show and dive into some formulas to cover those similarities, so we won't do that. Just, be aware of it. And then cosine distance. That one is a little bit different to describe. If you have an output from your model that has multiple values, so it ends up being a vector, and then that means you have your predicted vector and you have your true vector. So what cosine distance does is it treats those essentially as points in a multidimensional space, and it measures the distances between those. So the farther apart those points are, then the greater the error you have. So really, cosine distance should be small. A smaller cosine distance means that you have less error. And going from loss functions, now we can move into the optimizers. TensorFlow has a lot of built-in optimizers, which makes it really handy for us. That way we don't have to code any from scratch, and also that means less you need to know about them. So the built-in optimizers, at least the most popular ones, are gradient descent, atom, RMS prop, eta grad, momentum, and eta delta. The most basic one is actually probably gradient descent. That one takes the derivative of whatever loss function you're using, and it does that with respect to all the parameters that are built up in your model. If that doesn't make any sense, that's okay. You don't really need to understand that right now. The other ones are kind of fancier optimizers that oftentimes can be extremely efficient. Sometimes they reduce learning time, and sometimes they actually get you to a global minimum more easily. I'll actually show you here in just a second what a global minimum is. Before I do that, one thing to mention is momentum. While that is an optimizer in itself, these other optimizers can actually use something called momentum, and that just helps to kind of roll them out of little valleys that are local minima instead of global minimums. So here we have a nice illustration of somewhat how optimizers work. So really they're just algorithms that minimize the loss. So if we've already discussed the loss functions, what happens is these optimizers, they take you from a starting point where this surface we're looking at, where we have that start point, that's actually a surface for our loss. We don't know what that looks like, and neither does our algorithm. But what happens is they try to move it downhill, essentially. And sometimes you end up in a local minimum, which is a point of lower loss, but it's actually not as low as you can get. And the idea is to get to a global minimum. That's the lowest loss you can possibly have with the data that you have and the structure of your model. So the gradient descent algorithm, for example, that one moves you down a hill in the steepest direction. So whatever direction is the steepest downhill at any given point, that's what that one is doing. And then the momentum is used to kind of help to get you out of local minimum. So for example, you can build up momentum going down into that local minimum, and that would help you to get back out of it. And ideally, that'll help you to get into a global minimum. It would be harder to get out of given the momentum. Now that we've covered tensors and their operations, as well as loss functions and optimizers, we can move on to layers and how they fit into a model. Layers are usually just a collection of nodes that are composed of tensors and tensor operations. Most of the time they're connected in series, but some parts of models will have them connected in parallel. TensorFlow offers pre-made functions for creating layers in a model, which is much better than having to code them from scratch. Some of the common types are input, convolutional, pooling, dropout, and dense layers. Input layers are really just where you feed your data into the model. There's nothing special or functional about them. Convolutional layers can be 1, 2, or 3-dimensional, and they're generally used for computer vision tasks such as object detection, localization, overall image recognition, and classification. Pooling layers help to reduce the size or complexity of a model by averaging outputs from a previous layer. So what this does is it reduces the number of parameters, which makes computation easier. Dropout layers are used for regularization, which helps to prevent overfitting in a model. So what those do is they randomly disconnect certain outputs from the previous layer for each iteration as you train the model. And then dense layers, those are just the most basic kind of layers, and often you'll find them at the output of a model. Here on the left, we have a visual example of a neural network made up of 4 layers: the input layer, 2 hidden layers, and the output layer. The input layer is just the feed of our data into the model, so you can consider it to be non-functional. The hidden layers are any layers that sit between the input and the output, and they're where the majority of the work happens in a model. Each of the arrows that you see are just connections that are the outputs from the previous layer feeding into the nodes of the next layer. So we're not showing all of them, but you can consider this to be a fully connected network where we would actually have connections feeding from all nodes from previous layers into every node of each successive layer. So on the right, if you look here, this is an example of just one node. We have the inputs, we'll call them x, and those are the inputs from the previous layer. We have some activation function that operates, at least at a basic level, on wx plus b, where w would be the weights, the tensors mentioned earlier, and b, also a tensor, would be the biases. So whatever the activation function is, it'll operate on wx plus b, and it'll give us an output, and that output is what feeds into the nodes of the next layer. Now the output layer, that's where we actually end up with our predictions or our classification. And those have different activation functions. There's one in particular called softmax that gives us probabilities for our outputs. And those outputs feed into our optimizers. So that's where we have our loss function and whatever optimization algorithm that we have to compare predicted values to true values. And finally, we can move on to the last building block, which would be estimators. Estimators are a part of the higher level API of TensorFlow, and they handle a lot of work for us when creating models. They handle the training, evaluation, prediction, and building the graph. So for the training, normally that would entail iterating over a lot of batches of your data, feeding them through the network, connecting them to your optimizer, which is connected to your loss function, and then using those outputs and the loss in order to update the parameters of your model. So instead of having to do all of that by hand, it iterates over the batches for you, does all the training, and that way you can get the best possible output without having to code from scratch. And then evaluation and prediction, those are overall pretty obvious. Evaluation, just consider that taking a look at the accuracy of your model or computing the accuracy of it. And then prediction, if you have a set of values, set of observations that you want to feed into your model and get predictions, then you also don't have to write the code from scratch. Those methods are already built in. And building a graph. Well, you may want to build a graph for your model either on your local machine, or you may want to put it on distributed computing devices. Either way, that's handled for you by the estimators. Now that we've covered the major building blocks of TensorFlow, we're going to move on to installation. Before we have some live examples, we're just going to cover a few important points. On Mac and Linux, you're going to want to make sure that you have pip or pip3 installed. Which version depends on which version of Python you're using. If you have Python 2.7, then just plain pip is what you're going to be using. Whereas if you have Python 3, it actually depends. If you have Python 2.7 and Python 3 installed, then you'll be using pip3. If you have only Python 3 installed, then there's actually a chance that you're using just plain pip. All you have to do is go into terminal and type pip space dash capital V and hit return. If you have it installed, it'll tell you which version you're running. And if not, we're going to show you how to install that. Once pip is installed, all we're going to have to do is call pip install TensorFlow. And that will give us the CPU-friendly version that runs on CPU any, and that'll run on both Mac and Linux. And it's a much easier install. If you want the GPU version, that requires a lot more effort, and it only runs on Linux, not Mac. And that's because it requires support for NVIDIA GPUs, which Macs don't have. So for that, you would need the CUDA toolkit and cuDNN. That can be covered at a later date, or you can look up instructions for that one, but it's not required. Now for Windows, same thing, you'll want to have pip or pip3 installed. The installation of pip will be a little bit different, as you'll see. We have to download a getpip file, and once that's installed, the installation is also slightly different. Instead of just pip install TensorFlow, we would call pip install -- upgrade TensorFlow. And now let's move on to some live examples.